So tonight we're going to be continuing with what we started last time, which was talking about capacitors. I'll just refresh what a capacitor is for you guys. It's been a couple days, and we're gonna talk about combinations of capacitors. This is where we finished off last time. We talked about series, where capacitors are stacked up in a row, and we're going to talk about parallel now. And this will actually end up taking up almost all the class because we're going to just do a lot of problems to prep you for the homework, pretty much. Because most of the homework is basically doing stuff like that. So, yeah, let's talk about capacitors in parallel. Just to remind you what a capacitor is a device that tends to store charge, similar to the way that a spring might store energy. The capacitor is also said to store some type of energy. And we learned some relationships last time. There's really only one we learned, I guess, which tells us that the charge on a capacitor is equal to the capacitance, multiplied by the potential difference applied to the capacitor. And we usually think of a capacitor as something like a couple plates like this. This is always going to be the way you're going to see it drawn in a problem in physics. It might say something like, oh, you've got a capacitor and it has a capacitance of, let's say, 8 microfarads. The unit is farad. And it really... I'm sure this is like farad. Okay, what is this? Maybe that's confusing to you. It really just means the amount of joules per coulomb that it can hold. Sorry. Capacitance is, coulombs per joule. What am I talking about? Coulombs per volt. My God, I'm making you guys even more confused, I'm sure. It's the amount of coulombs that you can store per volt that's applied to it. Per volt of energy that's applied to it. All right. So, that's our capacitor. This is how we're going to see it in problems. What is it? Well, it's this thing that acts as like a gap in a circuit and prevents charges from flowing, and it's usually the case that there's going to be some amount of charge stored on it, some positive Q on one side, some negative Q on the other side, and we just say in general that the capacitor stores charge Q, even though in total it technically holds zero charge. Right? So capacitors in parallel. What is that? Capacitor in parallel means, suppose that I take a battery, draw it down here like this. Our batteries, we said we're going to be drawing with two lines, one that's long, one that's small, like this. The longer line is going to represent the positive side of the battery. This is going to represent the negative side of the battery. And in order to connect the battery up to a capacitor, we'll draw one capacitor right here, connect it directly to the battery like this. We'll say this one has a capacitance that we'll call C1, and we'll say the battery has a potential difference that we'll call delta V. This is going to be like the voltage of the battery. And then in order to connect things in parallel, what you do is you basically just kind of stack them on top of each other like this. Things are said to be in parallel in a circuit if you can draw... I'll do it like this. Like if you can draw a... It's so weird. I thought I closed that program. Interesting. So if you can draw like a line like this, and you can basically pass through the capacitor and then back to the battery in like one loop like this, and then you can do the exact same thing along a separate loop and go through the other capacitor here, like this, those are said to be in parallel. Okay? Like they each have their own connection to the battery is the way that I think about it. Let's undo those lines because we're not going to want those on there. Okay, that's when we say that they're in parallel. Now, our goal is to describe the way in which these capacitors can be reduced down into one capacitor, just like we did with the series capacitors. So our goal is to take this circuit and basically reduce it down to a circuit that only has one capacitor, the same battery down here, so delta V, and what we'd like to do is we'd like to find... Oh god, that looks awful. We'd like to reduce it down to one system, which is just one capacitor, that has the same equivalent capacitance of the two that are combined together. Okay? That's our goal. Now, when we talked about capacitors in series, we opened up this FET thing and we saw that they carried the same charge. And at the end of class last time, we used the same little simulation in order to show that when you have capacitors in parallel, they also have something the same. And what it's going to be is they're going to have the same potential difference. So each of these is going to carry the exact same potential difference, delta V. So this one on the top is going to have the potential difference, delta V, and this one on the bottom is going to have the potential difference, delta V. So our goal then is to come up with an expression of how we go from these two and relate it to over here. And what I'm going to say is that suppose that we define the charge that's on the upper capacitor plate to be Q2, because it's C2, and we say that the charge on the lower capacitor plate would be Q1. Then what I would say is that when we combine these together, this one is going to have a total charge, Q total, and the value of that charge, because charge is conserved, it's a conserved quantity, we can't create it or destroy it, really, then that means that Q total should probably be equal to the sum of Q1 and Q2. Does that seem reasonable to you guys? If, for example, the left side of this carries some positive Q2 and the left side of this plate carries some positive Q1, then certainly when we condense them down into one thing, we still must carry the exact same amount of charge on that left plate over here. So we look at our equation over here on the right, and it tells us exactly what the charge would be. So Q1 should be equal to the capacitance C1 multiplied by delta V, and then Q2 should be equal to its capacitance multiplied by delta V. Right? You take the capacitance, you multiply by the voltage, and that tells you how much charge is actually stored there. So then when we come back to the picture down here, we say, okay, well, the total charge should be equal to the equivalent capacitance, CEQ. You could think of this as total capacitance if you want to. I don't know if there's any better way to do that. Whatever you want to think of it as. And then we'd multiply by the voltage, which is delta V right here. And then we'd see pretty quickly that delta V shows up in every single term. We can cancel that out, and we're left with this expression that tells us that the equivalent capacitance is simply given by summing up each of the capacitors in this case. And then, like, in general, if I have, like, 5 capacitors and they're all attached in parallel like this, the equivalent capacitance would, you just sum them up, right? So in general, we say that for capacitors in parallel, the equivalent capacitance is given by C1 plus C2 plus C3 plus however many you have in a circuit. That doesn't look like what I was trying to write. Capacitors connected in parallel. Okay, so we've introduced like a new language here with this word parallel. It doesn't mean the same thing as parallel from mathematics, but in a way, these lines kind of look like they're parallel. They wouldn't necessarily have to be. For example, I could slide these capacitors around a little bit and it wouldn't change the system at all. So just to give you an example, I could have a circuit like this. These are also parallel. So here's your battery, here's your C1, here's your C2. This is technically exactly the same circuit as the one that I've drawn over here on the left in terms of the circuit diagram. And that's something that's going to kind of come to place with some problems that we're going to look at a little later. But in general, you can think of these capacitors as you can basically slide them anywhere you want along this outer connection point here, as long as you don't cross over these junctions. As long as you don't cross over a junction. So the way I think about it is, imagine that these are like wires, and these capacitors are like little beads that can slide on the wires, but they're constrained to slide on the wire. Then this bead C2, you can imagine you could slide it anywhere you want to up here, and it doesn't physically alter the scenario in any way. Because after all, it represents connections with wires. And yeah, does that make sense? You can basically slide them anywhere you want, and it doesn't affect it, that this is parallel, this is parallel. Yeah. Does that make sense to y'all? Does anyone have any questions before we start solving problems with these things? So we are going to start with this problem from your textbook. We'll do 2 that are kind of simple, and then we'll jump into some that are a little more challenging. So our goal is to see what happens when you have capacitors that are connected both in series and in parallel, and use that to calculate what their capacitance is. But one additional thing that we're going to do is we're also going to calculate the charge on each capacitor. We'll do that afterwards. Okay. So here's the problem. You guys can read it. Find the equivalent capacitance of a 5 capacitor network. You have these 2 points. This says A. I just got clipped. 2 points A and B. A 9 microfarad capacitor, then a 3, an 11, and a 12 and a 6 connected together like this right here. And our goal is to find equivalent capacitance. All right. I'll remind you kind of quickly that when you have capacitors that are connected in series, the way that we found that we can find their equivalent capacitance is by using an equation like this right here. You add up the individual capacitors' inverses, and you take the inverse of that. Right? So, coming to this problem right here, and I should make it a little bit bigger for you guys, I think. So, we're going to break this down step by step, and we're going to do like several steps to do so. So what I'm going to do is we're going to say, we notice these 2 capacitors right here. How do they appear to be connected to you guys? Series, that's right. So you could imagine that we could take these 2 guys, these 2 capacitors here that are in series, and we could write their equivalent capacitance, right? So let's do that. So let's redraw the circuit. We'll leave everything the same other than those 2. So we've still got our 3 microfarad right here. We've got the 11 microfarad right here. And we're now going to replace these 2 with one new one right here. Leave a little bit of room here. And then out here we've still got the 9 microfarads sitting here too. So we've got 9, 11, 3. And you guys tell me, what would this one be? You got 4, okay, and then how did you calculate that, Ash? You do the inverse thing, right? So we're going to do a 1 over a 6 plus 1 over 12. We're not going to worry too much about the units here. Everything's in microfarads. Just be a little bit careful. And if you do 1 over 6 plus 1 over 12, a 6th plus a 12th is the same as 2 over 12 plus... So this is the same thing as like 3 over 12 to the negative 1, which is 1 over 4 inverse, you get 4. So yeah, that's right. This is going to be 4. All right. Any questions? Okay, we want to reduce it down again. Then we look at these. There's another line right here, right? Let's keep this thing together. So this was B and this is A. We'll use that later. So now we've got 3, 11, and 4. And they're all connected in what way now? Parallel, that's right. So what's the equivalent capacitance of these 3 going to be? Our rule for parallel says we do what? We just add them together. So 11 plus 4 is 15. 15 plus 3 is 18. That's right. So now what we have is a much simpler circuit. All we have left is the 9 microfarad right here. And that whole series of 3 capacitors can be simplified down to just one capacitor that's going to have 18 microfarads. A, B, and then we can simplify them down one final time into just one capacitor. And that capacitor will have the total capacitance of the system that we're going to call CEQ. And what's that one going to be? You guys want to do that calculation? It's going to be 6th. That's because you're doing 1 over 18 plus 1 over 9. You get common factor here. That's going to be 3 over 18 to the negative 1, and that'll give you 6. So our final answer here is that it's 6 microfarads. That's pretty much all there is to these problems. It's pretty easy. It can get a little trickier. We'll look at that in a second, but if you can do that part, you should be set on doing the next part. So this would be, we'll call this as part A of this problem. And we're going to add our own part to this part. So now we're going to say, if the potential difference, delta V, between A and B is, let's say 10 volts, we want to find the charge on each capacitor. All right. If the potential difference between A and V is 10 volts, find the charge on these capacitors. What does that mean? That would mean, like, suppose that I connect up a battery here. Oop, like this. And I tell you that battery has a potential difference of 12 volts, or 10 volts. Find the charge on all of them. Does the question make sense? So the way that we go about this is you start from the end. You write out all these steps that we just did, and we're going to go backwards. We're going to say, if this is subjected to a delta V that's equal to 10 volts, and it then carries some charge that we call Q, what would Q be equal to? For all the questions that I'm about to ask, you only need to know the one formula. Q equals C times delta V. And then a couple of rules that I'll say as we go along. So what would the charge be here? 60, right? 60 microfarads, or 6 times 10 to the negative 5, that's correct. All right. So let's see if you can figure the next part out. If this one carries a charge Q equal to 60 microfarad, and I go backwards now, how much charge do y'all think will be on the 9 and the 18? Is it going to split up? Is it going to be equal? Is it going to be, like, yeah, how is that charge here going to be compared to the charge on these two? There's a rule that we equal. That's right, Ty. Exactly. These will have exactly the same charge. So this upper one is going to have a charge of 60 microfarads. The lower one is also going to have a charge of 60 microfarads. And that's possible because they're going to be alternating. Like, if this is plus and this is minus, this will be plus 60, this will be minus 60, this will be plus 60, this will be minus 60. So when you add them all together, you haven't added any new charge into the system because the ones in the middle kind of have total charge of 0. Farads are equal to C. Farads are the unit of C, if that's what you mean. Farads are the unit of C. Oh, you know what I did wrong? You're right there. That doesn't make any sense at all what I wrote, because this is the charge. So sorry about that. 60 coulombs. Sorry. I'm so sorry. Yeah, this should be coulombs. So this is something to remember when you're doing these problems, that, like, when they're in series, objects have the same charge. So when you go backwards from this final diagram to this diagram, you say, oh, they're in series, they have the same charge. Okay. So we've now already answered one of the questions. It said find the charge on each capacitor, right? And we now know that this 9 microfarad one down here, it carries a charge of 60 coulombs. Okay. What about all these other ones? So again, we want to go backwards, and we're going to use the information that we've got here to find something out about these three guys that are in parallel here. Nathan's question is, so if they have the same charge, the capacitors in series would differ in distance and or size. Sure. Yeah, the 18 microfarad and the 9 microfarad would be different. Is it microcoulombs? Yeah, it's microcoulombs. You're exactly right. I'm so sorry. Oh, and I did it over here too. Oh my god. I'm confusing you guys. I apologize. Microcoulombs. 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 Thank you for noticing that. Yeah, you're right, Ash. I'm sorry about that. Okay. So going back here and looking at these three guys that are in parallel, what information do you think we can take from this picture here and apply it to these three that are in parallel right here? Any ideas? Delta V should be the same, exactly. These three are in parallel, so they should have the same potential difference. And how can we figure out? They're actually going to have different charges, as it turns out. The charges are going to distribute kind of depending on the size of the capacitor here. But they will have the same delta V. How do I figure out what delta V is going to be? They will add to 60. Correct, Tyler. That's right. Just different proportions based on the size of the capacitor. So, how do I figure out what delta V is going to be for these? V equals to Q over C, exactly. So for us here, we'll just put it right here. On the one on top right here, just not much room. I'll choose a different color. So delta V should be equal to Q over C, so 60 over 18. See, 6 over 18. Interesting. What's this going to be? So they're both factors of 6, so it's like a 3. And so it's like 10/3, so it's like 3.33, right? Does that sound right to y'all? 3.33 volts? Okay. So now we know that this one is going to have 3.33 volts. This one has the same thing. This one has the same thing. And so now we could go through, if we know what their voltages are, right? We could find the charge on each one, right? By doing, again, this. By multiplying 3 times this. So this one, I think, would have something like 10 coulombs. This one would have something like, I don't know, it's 11 times 3.33. This is going to be like 3.63 something or something like that. Yeah, 36.7 coulombs. And then that one is going to be 4 times 10/3, so 40 over 3, which would be like a little bit less, so it's going to be like 13.33. And as someone mentioned, if you add these three numbers together, you should get 60, okay? Likewise, if we went back to the previous part where we said the delta V on this one was 3.33, delta V on the one below is going to be 6.67. So you can see that the voltages add together to give you this voltage, and then the charges here add together to give you the total charge right here. Okay? Does anyone have any questions? So going back one more step, just continuing the same process until we're done, we notice that these two are in series. Can anyone tell me what the charge on the 6 microfarad is going to be? 13.3. Multiple people chimed in very quickly. That's right, and it's because we know that when they are in series, they have the same charge as they did when you move them down to just 1. That's all there is to this. It's pretty simple. It's an algorithm. You should be able to replicate it for yourself. And all you need to do is you need to remember this, and you need to remember series, same charge, and the other thing to remember is parallel. You get the same potential. That's it. Yep, exactly what Nathan just said. Series, same charge, parallel, same voltage. That's all you need to remember. Remember that. Remember this. You're good. So we'll do one more of these that's kind of easy, and then I'm going to give you guys 2 of them that are a little more difficult to work on. And I think I showed them to you last class. So we'll do one more that's a little easy right here. We'll do this one probably a little quicker, as quickly as I can without being too sloppy. All right, maybe I guess I'll make it a little bit smaller. Okay, this is from a different textbook, but it's basically the same idea. Find the equivalent capacitance between the points A and B in the figure, and then it says if the potential difference is 120 volts, what is the charge on each capacitor? All right? So again, pretty simple. All we need to do is to take our system here and reduce it down. In this case, we've got a 4 microfarad and then a 1 and a 3 that are kind of branched off like this, a 6 and a 2, and an 8 right here. Everything's in microfarads, as it says up here. So how does that break down? So the first thing we can do, the easiest thing to do, and you don't want to do too many things at once, is to take those 2 that are circled there in gold and break them down into 1, and take the 2 on the bottom that are circled in gold and break them down into 1. So this is a 4, 3, and 1. What's the equivalent capacitance of those going to be? The 3 and the 1, when we combine them together, what's the equivalent capacitance going to be? 4, that's right, you just add them. Down here, 6 and 2, you add them together, you get 8. The other one already was 8. Reduce it down further, we're going to be left with the 2 on top. Now, here's where you don't want to do too much at once. It might be tempting to think you can take the 2 on top and the 2 on bottom and say, oh, they're all parallel. But that doesn't work. So you have to combine them down one at a time, like this. The upper one here is going to be 1 over 4 plus 1 over 4 to the negative 1, which I think you can see pretty quickly is 2. Is it? A quarter plus a quarter is a half, 2? Yep. And this one is going to be 4, because it's going to be an eighth plus an eighth. The numbers in this problem are very forgiving for doing this, but it makes a good way to do a problem kind of quickly before we move into something harder. And then we reduce this down one more time into just 1 capacitor, and that capacitor will have, they're in series, or not, sorry, they're in parallel, so we get 6. Pretty easy, right? You put the battery on the A or the B. Well, both. Remember, batteries have 2 contact points, right? So you put your battery here. Right? And this is 120 volts. And so from the very end, we say, okay, delta V is going to be 120. And then the Q, which is equal to, again, remember the equation, Q equal to C times V, or Q equal to V times C, however you want to remember it. So the charge here is going to be 6 times 120, which should be what, like 720 microcoulombs. We go back this way. What's going to be the same? Every single time you do this, there's going to be 3 numbers, like 1, 2, 3 numbers, right? And one of those 2 will always be the same when you go backwards, right? Which one is it going to be here? V is the same because they're parallel, right? It's never going to be this one. So it's either V or Q, right? So now we know that V is the same on each of these. So we go ahead and write here. This one's going to be delta V equal to 120, and I guess I can say that applies to both of these. So then in order to find Q, we again do just C times V, right? Yeah. So this one is going to be Q equal to 2 times 120, so 240. And 4 times 120, this one will have a charge that's equal to 480. Those 2 should add together to give you this. That's one way you can kind of check that you did it right in case you made a mistake. Okay, go back one more step. Again, always something's going to be the same here as we move from this back to this. What's going to be the same on the 4 microfarads here? It's going to be Q, because they're in series. So we know now what this charge is. So these 2 both have a charge of 240. And These two will have a charge of 480. And then in order to find delta V, we do Q over C. So we do 480 microcoulombs, and we divide by 8 microfarads, sorry. And that should give us delta V. 8 goes into 48 6 times, so this is going to be 60 volts. And then up here, we're going to have 240 divided by 4, so delta V. Hold on a second. Yeah. No, we're good. It's just kind of weird because they're both 8. Okay, we're good. On the upper one, it's going to be 240 divided by 4. Is that also 60? Guess that's okay. Yeah. That bothers me a little bit. Is that accurate? Did I do that right? No one's saying anything, so I guess it's okay. 8 goes into 48. This is 60, right? Microfarad. So we're doing, what is this? So we're just doing 240 microcoulomb divided by 4 microfarad. That's 60, right? Looks right. The micros kind of cancel out, Mr. Meowers. Yeah. They both are 10 to the negative 6. Anyway, it works out. I mean, 60 plus 60 is 120, so that passes that test at the very least. And now we got to be careful as we go back to the original picture, which is a little bit smaller here, because now we've got, we know what delta V on each of these is. So delta V for these two right here will be 60. Yeah, each of these is 60, right? 60 volts, 60 volts, 60 volts, 60 volts. They're parallels, that's okay. The 60 plus 60 gives you 120, okay. It's because they're all equal that it's all kind of weird on this one. So coming back to this one right here, we know this is going to be 60 volts for both of these. So the bottom one should have a charge of 2 times 60, or 120 microcoulombs. The upper one right here should have a charge of 60 times 6, which would be what, 360. And then up here we're going to have 3 times 60, so this one's going to have a charge of 180. And the upper one's going to have a charge of 60. And all of these, if you add them up, should work out properly. Like 120 plus 360 is 480. And 60 plus 180 is 240. So we're good. Everything, there's no violation of charges appearing or something like this. Anyway, that's all there is to these problems. And I'm going to give you 2 to work on that are a little trickier, but that's pretty much it. Any questions before I set you guys to working? Does that kind of process make sense to y'all? Okay, so what I would like for you to try to do is to do these 2 problems here. So it's this one and this one. I'm gonna have to add one thing to one of these 2. It seems easy for now, he says in italics, yeah, exactly. These 2 are a little trickier, but I will say if you can do these 2, you can do any of the ones in the textbook, or any of the ones in the lab manual for that matter. Although I do not believe I assigned lab manual problems with these problems, or with these type of problems, as far as I know. At least I don't remember doing so. So I would really like for you guys to try to do both of these. If you would prefer to like hop to a different channel, there's I could make more channels, but there's the 4 channels in the bottom if you want to like work in groups or something like this. But I kind of like to give you guys an extended amount of time to try these problems. So you've got 2 different pictures here. Your goal is to find the equivalent capacitance, and in both cases, I'm going to give you guys. Let's see. We're going to say for this one, let's say we'll say delta V. We'll just do 100 for both of them. So say delta V is 100 volts for both of these. So basically, you want to do exactly what we do before. So we want to find the equivalent capacitance as it says in the problem, but also we want to find the charge on each. So I think I'm going to give you guys like 15 minutes, because then it would be 6:55 and we can come back and talk about the answers. Does the order matter? No. It should work no matter what order you choose, Ash, as long as you do it properly. So find the charge on each capacitor. Same thing in both cases. Like, I guess I'll work it out myself, because my notes for this stuff are probably at school. Okay, does that make sense? Try both of these. If you get stuck on one and you can't figure it out, that's fine. You go try the other one. But keep in mind that there's some things here, especially with this one, where it might trick you a little bit. So I want to emphasize that you are free to move the capacitors anywhere you want. You can redraw the diagram however you please to make it more to make it clear to yourself as to what's going on. You can even do things like take these connections right here and shift them around, as long as you don't alter things. Like, this is a huge hint, but this wire right here that's connected to the corner, you could flatten the corner if you want to. You could take the wire and you could connect it somewhere along this line. You could take this wire and connect it somewhere along this line, and you wouldn't change anything. What was the corner point you said we couldn't go beyond earlier? You can't go beyond. Okay, so you're free to move the. Again, think of this as like a bead, and think of these as like frames along which the beads are moving. You know, like those like little toys that they have in, I don't know, doctors' offices was where I'm seeing. Like, you have these little beads that would like slide around these frames, and like you just can't go past the joints. Does that make sense? So I can move C2 anywhere I want on this line. I can't move it. You can move it left of C1. I don't think it would change anything, but you cannot move C2 over to like the other segment here. Right? I can't move C2 up into the segment right here. And same thing with C3. C3 is basically stuck between these 2 points. But otherwise, you can completely alter the circuit as much as you want. And keep in mind that these are wires and they can be bent. So I could bend this wire any way I want to here, like flatten it if you want. Branching points are no-goes. Exactly. You just cannot. You can't move past the. Corners are fine to change. You can move things around corners. You just can't move them past the branching points. Exactly. Think of these as like intersections. And this is like a car, right? And you're just not allowed to turn, I guess. All right, so take 15 minutes. In like that amount of time, I'll come back and check on you. And we'll just... I'm here, so if you have questions, I'm going to be watching. But I'm also going to be kind of like looking down and writing to try to solve. If you prefer to do that, Mirage, you can. If you just prefer to just work at your desk, and that's fine too. But yeah, if you want to talk about it and you want to go to another channel, like, yeah, feel free. It's been 15 minutes. Do you guys need a few more minutes, or? Okay, do you want to go ahead and start to solve them, or do you want just a little more time? Just let me know. Okay, we'll get started again in 3 minutes. I'm gonna go ahead and start just moving things around on the screen. Okay, it's 7 o'clock, so let's try to solve these out. So what about just the first part, the equivalent capacitance? Did anyone get an answer for this one? Anyone brave enough to type what they got in the chat? 6.05. Anybody else get the same thing? Yeah, good. That's good. That's really good. So let's do the whole process. What did you figure out? How are C1 and C2 connected? Are they in series or parallel? Yeah. These are series. Good job. These are series. And when we connect them together, we end up getting something like this. So we'll have... Apologize if that was a loud noise for you there. And then these two are connected in... how are these two connected? The C2 and the C2, those are pretty clearly parallel. Shouldn't have been much question about that. C2 is 10, so this becomes 20. The C1 and C2 are 5 and 10, so this is a fifth plus a tenth, and you take the inverse. You end up getting 3.33 for the outer ones. So this is 3.33, this is 3.33, and of course the inner one is still whatever it was, 2, right? C3 is 2. And then from here it's pretty easy. The 3 right there are connected in, these 3 are connected in parallel, so you just add them together. So you end up getting 8.66 or 8.67 microfarads. And the bottom one, you're going to get, well, so 20. And then we just reduce that down to one final one right here. It's 20 microfarads. There you go. Nope, 20, not 20. The answer that you guys got. From the last one, you got to do, what is it, 1 over 8.67 plus 1 over 20. Take that to the -1, and you'll get 6.05. As you all said. So really good job. If you got that just after the short lesson we did today, I think that's really good evidence that you know what you're doing, and you shouldn't have too much problem on your own. So our equivalent capacitance is 6.05 microfarads. If that was... That's all the problem asked us to do. But I also said, suppose that delta V on this one is 100 volts. Now you want to find the charge. Once again, we're going to be using this general equation that Q equal to C times delta V over and over again. So you end up getting Q equal to 605 microcoulombs right here. My hand's really cramping. I don't know why. These two will have exactly the same charge, so this is going to be Q equal to 605 microcoulombs. They have the same charge because they are in series. You find the voltage, delta V, on this one. We don't need to do this one, right? Wait, do we? Yeah, we do, right? Yeah, so delta V for this one is going to be Q over C. So it's going to be 605 microcoulomb divided by 20 microfarads. I might not have calculated that, did I? No, I did. This is 30.25 volts. And then the upper one has the exact same charge, so you find delta V by doing 605 divided by 8.67. That gives you 69.8 on this one. You come back to here, you say these are all 3 in parallel. That means the delta V for all 3 of them is going to be 69.8 volts. The one below, nothing's changed, so it's still 30.25 volts. You do 69.8 times 3.33, and you get Q equal to, I got 232.7. Please tell me if any of these numbers that I got are different from what you got. Does that look right? Just take that times that. Okay. So that's going to be 232.7, and then this one will also be 232.7 because it's the same. And then since these were in series, you end up with 232.7 microcoulombs on this one, as well as the one above, and this one. They're all the same. And the one in the middle, we know 69.8 volts for this one, so you do 69.8 times 2, which is like about 70 times 2, about 140, or more specifically, I got 140 for this guy right here. And that translates back to here. So we've got 140 microcoulombs on this one, 232.7 on all the rest of them, and then finally for this one here, we know that 32.25 volts is going to be the voltage for both of these. So if we take C2, which was equal to, I believe, 10, making this calculation super simple, we get, 302.5 microcoulombs. I gotta find a better way to write. My hand is really cramping up as I do this. I think I'm just writing fast and it's doing that. I don't know. Okay. Any questions? This is hard. This is as hard as these problems get, but I hope you guys feel like this is also pretty straightforward. I'm not going to say it's easy. It's a physics problem. Nothing in physics is easy, but hopefully it's straightforward enough. Any questions about this one? Yeah. See, this is the best part of 1C. For the yeah. I'm still recording. It's being recorded, and I'll put it on YouTube so you can go back through and, because I obviously did that really fast. You can slow it down and pause and see how this stuff developed. Yeah. It is more straightforward than Gauss's law, and I want to emphasize, like, if you've been a little overwhelmed with the homework problems up till now, I promise you they really are getting easier for a few weeks. And they'll get hard again, and they'll get easy again. So, okay, let's try. It really will. So we'll do capacitors, then we'll do current. That'll be pretty easy, and then we'll do DC circuits. It'll be a lot of the same stuff with resistors instead of capacitors. We'll put resistors and capacitors together and talk about those, and it won't get that much harder. And then what's next? And then we'll eventually, when we get to magnetism, that's where it's going to get hard. No, AC is actually pretty easy. That's when it gets easy again. The last two chapters are pretty easy because AC takes us back to this kind of stuff. What gets difficult is when we introduce magnetism, and now we got to talk about how magnetic fields are produced. But then once you understand how they're produced, the problems are pretty easy actually. Like they're I shouldn't say that. They're not easy, but they're doable. I promise that I can show you how to do them, which I think is at the very least good. It doesn't mean it'll be easier for you, but like you'll at least be able to like kind of see the process, and I think I can show you again kind of an algorithm by which you'd solve those kind of problems. Gauss's law, there is no algorithm. That's the problem. There's no just one size fits all solution. You've got to be creative, and you've got to think about like the way things look three-dimensionally. Okay, what did anyone get the answer for this one? What did y'all get for this one? Get an answer? Didn't have. That's fine. Maybe somebody did. No? Ah, yes. There you go. 12.9. That's good. Maybe did you work on? Just be honest, Ty. Did you work on it before class? Because I know I put these problems up, like they're available. Because I didn't think 15 minutes was enough time. Like I was furiously writing quickly to try to finish the time. So, and I've done these before, so I don't think it's much time. So the tricky thing about this one is you need to figure out how to rearrange it. And I gave you a couple hints, but you probably spent more time working on the first one. The trick for this one is that I can take this connection here and this connection here, and I can basically shift it all the way down to there without changing anything. And this one all the way up to here without changing anything. And then I can kind of like tilt it. So to put things really simply, what it ends up looking like is this. It's actually a really simple circuit when you redraw it. So you've got your upper 4 microfarads up here. And then you've got your 5 and 7, and those actually end up like right here. And then you've got your 6, and that ends up down here at the bottom. And now it's like a super simple circuit. It's really easy now. And if you just didn't immediately see that, that's okay, because these problems are really just about trying to understand what these diagrams mean. Yeah. But this is how it would reduce down. And now you've got 2 in the middle that are in series, right? So this can be reduced down into a stack of 3 in parallel. And I believe the one in the middle ends up being, so it's going to be 1 over 5 plus 1 over 7. So 1 over 5 plus 1 over 7, 2 prime numbers. There's no way this is going to be simple to reduce. This just becomes 35 over 12, which is 2.92. So we end up with the 4, 2.92 right here. Sorry, it's kind of small, but you can see it right here. And then at the bottom, 6 microfarads. Okay. And of course, these 3 are in parallel. Let's go down this way. So they become just 1 capacitor. And it's 10 plus 12. So 12.92. And that's it. We do the charges. Q is going to be equal to 12.92 times 100, so 1292 microcoulombs. These are in parallel, so they're all going to be 100, so this is going to have a charge of 600 coulombs. Did I do all these? Yeah, I did, okay. 600 microcoulombs, 292 microcoulombs, you just multiply by 100, super easy. Coulombs, and 100 microcoulombs. And we're done, because these two are in series, so they're also going to be 292 and 292 microcoulomb. Pretty easy. Once you know how it looks, the hardest thing is just realizing how to redraw it, but once you redraw it, this is a pretty simple circuit. Actually, they both are, technically, once you redraw them, but, yeah. It's easy when you know the answers, I guess, so. Or at least know the process. I didn't know going in if my answers were right until I asked you guys. Because actually, when I first did this, and I got this as my answer, I was like, that doesn't sound right, but I guess it is. Okay, so that's, you know, capacitor problems. That's pretty much all there is to it. There's a couple topics we haven't discussed yet, and we'll finish those up next time, but they're going to be really short. It'll take us less than 30 minutes or so. We'll talk about what a dielectric is, and we'll talk about energy stored in a capacitor, and then the energy of the electric field itself, which is kind of an interesting topic that will be something that will kind of show up way later when we talk about light. Because light actually has energy that it carries inside of fields. Ty says, remember that conductors have the same delta V inside of it, and that's the key of this problem. Yeah, you're right. You're right, that is the key. What's the conductor here, Ty? It's the wire, right? The wire. That's really a good way of putting it. The wire is a conductor. So you don't change anything by like changing where the wire connects to another wire that has the same potential. The same V. You haven't changed anything, right? We know, like, if this was 100 volts and this was 0 volts, every point along those wires is also going to be at 100 volts, at least until you get to your capacitors, right up to the edge. So it's okay to kind of rearrange it, and you don't really change anything. I believe you could even take this wire and you could connect it, like, right here. That wouldn't change anything either. Like, I could have, like, this wire that's connected to the corners right here, which they're not even really corners, right? You could squash them down and make them whatever you want, like we did over here, but this wire could literally be connected. Let me erase this. That wire right there, you could literally connect it like that, and it'd still be the same circuit. You could connect this one way down to here if you want, and it would still be the same circuit. It just doesn't change anything at all. So of course it's okay then to just connect them up to right to the corners and then squash the corners, bend it, whatever. A real circuit's not going to look like this anyway. It's going to be a bunch of wires, right? So, okay, I'm going to stop the recording for now. I will answer your question, Ash, though, off the thing. If I can find my thing. There we go.